This video is collisions in two dimensions 1. Write an equation for each statement. Net force is the time rate of change of momentum. Net force is the time rate of change of momentum. How about the second one? Net force in the x direction is the time rate of change of x momentum. F net in the x direction is equal to the time rate of change of momentum in the x direction. If we want to put vector symbols over the f and the momentum variable, we can do that, but the x kind of takes care of that as well. So I'll leave that up to you. Similarly, the net force in the y direction is the time rate of change of y momentum. Let's summarize what we just did there. If there is a net force on a system, then the momentum of the system will be changing with time. That is, the system's momentum will either be increasing or decreasing as time goes on. On the other hand, if the net force on a system is 0, then the time rate of change of momentum is 0, which means that the initial and final momenta are equal. Only in this latter case is momentum conserved. One more time, let's write this equation that we've been dealing with here. The net force is equal to the time rate of change of momentum. So if there's 0 net force, then the momentum must not be changing, which means it's conserved. If there is a net force, then the momentum is changing, and we can't use momentum conservation in that case. But let's try one example problem, and what we're going to find here is that momentum in the x direction is conserved and momentum in the y direction is conserved as well. We have an overhead view here of two masses, and they are going to collide right here. They have given masses and given initial velocities, and we are told that they collide in a completely inelastic collision, which means they're going to stick together. And the question is, with what velocity do they slide off together here? We know, based on just common sense, that the direction of the velocity is going to be somewhere up and to the right here, based on what we are given. So what we're going to do is we're going to conserve momentum in each direction. Let's do the x direction first. The x momentum initially is only in mass A. Mass A only has x momentum, and mass B has 0x momentum. So the total x momentum of the system is just the mass of mass A times its velocity. I'll put the units on here in just a second. 9 kilogram meters per second. That's the total x momentum of this two-mass system. What about after the collision? After the collision, both masses are stuck to each other. So that means that the total mass is 1 plus 2, or 3 kilograms. And that combined mass is going to have a final velocity in the x direction. I'll call it vxf. Momentum is conserved. So that amount of momentum right there needs to be equal to that amount of momentum, which means that vxf is 3 meters per second. And because it came out positive, we know that it's to the right. We repeat this for the y direction. In the y direction, what's the initial momentum in the y direction? The initial momentum in the y direction is due only to this mass here, mass B, because mass A does not have any y momentum to start with. So momentum, as we remember, is generally mass times velocity. That's in the positive y direction. So the initial momentum in the y direction is 12 kilogram meters per second in the positive y direction. At the end, the y momentum finally, the total mass that is going to be moving, once again, is 3 kilograms, and that 3 kilogram combined mass will be moving with some final y velocity. Well, that final y momentum must be numerically equal to that initial y momentum. So 3 times what equals 12? Well, that means that Vy final equals 4 meters per second in the positive y direction. So then, if we just use the Pythagorean theorem, I'll sketch this out very quickly here. We've got Vx final is 3 meters per second. We've got Vy final being 4. So our final velocity, V final, which is what we're after here, is 5 meters per second. And if we remember our angles, this angle right here is going to be 53 degrees above the positive x-axis.